Hello and welcome to my third example in this course. As you can see, I wrote some things over here to explain a little bit. I already started to make this video and to film, and when I filmed and recorded this video and I started to explain, phone rang and I had to call, so I had some problems and I didn't want to remove all of this, so you know, don't now concentrate on this, and this. Just concentrate on the example. Now, the example says consider. So here you have consider the transformer from example number 2. So if you didn't watch my not previous but before that one video, I did an example and you know, we had a transformer with some ratings. For example, this was the first. It was a 10 kilovolt ampere transformer. It had 2200 volts on the primary side, 220 volts on the secondary side. So these are the rated voltages, and you know that the turns ratio for this is this divided by this, and that is 10. So and we had rated currents. I on the high side, the current on the high side, rated current on the high side was 4,55 amperes. On the low side, 45,5 amperes, and that's kind of it. So you don't have to know what was going on in the second example. I just this here were the rating. This here was the transformer rating. So now it says that. We have to determine the voltage regulation in percent for the following conditions. So we have two conditions: 75% full load, 0,6 power factor lagging. Same as A, just power factor leading. And for C, we have to draw the phasor diagrams for A and B. Now, so 75% of full load, that is 75% of the rated current. So on the high side, or the transfer value from the low to the high side, that is equal to 0,75 times 4,55, and that's 3.41 amperes. So, but now it has power factor, cosine of theta 2 is 0,6. And the angle of the load, that theta 2, is plus or minus 53,13 degrees. So the inverse arcus cosine of theta 2 of 0,6 is plus or minus 53,13 degrees. So the minus sign is for lagging and the plus sign is for leading. Now, here is the schematic over here. Now we have the high voltage and we have the low voltage terminal. Now, in this situation, we will have a constant voltage on low voltage terminal, which is equal to, because this is referred to the primary side, we will have 2200 volts, zero phase degrees. Why? We'll see later why. But this high voltage changes. So you will see how much of this high voltage we must bring on this side, so that the load will be 2200 volts and zero phase degrees. So this here is a constant and it doesn't change. So this here is the 200. Sorry. So the low voltage terminal, but referred to the primary side, is 2200 volts, 0 degrees. Shifted. Now, these are the values from the example number 2, and this is the equivalent internal impedance of the transformer from the high voltage side, and the value of that was 10 comma 4 plus J 31 comma 3 ohms. Okay, so this was the internal impedance from the example number 2. Now you don't need to remember it. I'm just using those parameters for this example. Now, as you can see, here we have the high current, or IH or IL prime. So, and its amplitude is 3,41, but it has a power factor. So this here is the magnitude of the current, but the complex value of the current here is equal to 3,41 in brackets here, cosine plus or minus 53,13 degrees plus J sinus plus or minus 53,13 degrees. So this is the complex value of the current. Now we're gonna do first for A over here. Now for A, we need to calculate what is the high value of the voltage. Now we said that here this is 2200 volts, zero phase, and now we have to calculate the complex value of the high voltage side. So we're gonna do that with calculator. So this is for minus 50, because it is lagging, we're using minus value. So minus 53,13 degrees. Now you just use a calculator. First, what you do, I calculate cosine of minus 53,13 degrees. I get 0,6 value, and like this, and then I multiply it by 3,41, and that is 0,064 plus we use J sine of minus 53,13 degrees. So in my calculator I click sine, then I click minus, then I type minus 53,13 degrees. I get about minus 0,7999 for the sinus minus 53,13. Then I multiply this with 3.41. I get minus 2,727, but I mustn't forget the J sine. So this here is the imaginary part of the complex value of the high voltage current. Now you get that IH, this here, I'm just gonna write this down, 0.46 minus J 2,727 multiplied with 10.4 plus J 31,3. And now, I don't want to make this a long video, so this here is only math, and I'm not gonna do that. So I think you already did this in basic electrical engineering or in mathematics complex numbers. You can easily calculate this, and then in the end you get that the high voltage here is equal to 2306, 94. So this is the amplitude of the voltage, and its phase is 0,9 degrees. Now, what is the voltage regulation? This here acts as a no load value. This here acts as a no load value. So this is the formula for the voltage regulation. If you watched my previous video. And now, that is equal to 2306,94 minus 2200 divided by 2200. And then you get that the voltage regulation is 4,86%. I forget to multiply by 100%, but I think you know this. Now, what this is saying to us? Now, the voltage regulation 4,86%. The meaning of 4,86% voltage regulation is that if the load is thrown off, the load terminal voltage will rise from 220 to 230,69 volts. In other words, when the 75% full load at 0,6 lagging power factor is connected to the load terminals of the transformer, the voltage drop from 230,69 to 220 volts. Now, if you have a transformer, if you bring this on the primary side to 2200 volts, on the secondary side where there is no load, then you will have this, but only 10 times less, because now this was referred to the primary side. So you divide it by 210, because the turns ratio is 200. The turns ratio is 10. Now on the secondary side, we don't get 220 volts. This is the rated voltage, but in the no load voltage will be 230,694 volts. Not 2000, but just divide this by 236. You divide this by 10, and then you get 230,694. Now, if you bring a load that has 0.6 power factor lagging, so you have some inductances, or for example a motor, then this voltage on the no load voltage will decrease from 230,694 to 220 volts. So this is the meaning of the voltage regulation. Now let me just write down, draw the phasor diagram for this situation. So now we have referred value, the load value, VL prime, with an amplitude of 2200. Now, the high voltage is shifted 0.9 degrees, as you can see like this. And its amplitude is 2306,94 volts. So between the high voltage side and the referred load voltage, you have 0,9 volts. from here to here, this is the current IH, which is equal to IL, refer to the primary side. You have a phase shifting. You have a of minus 53.13 degrees. If it was if it was plus, it will go on the other side. And now you have some resistive. You have this here vector is IH times R equivalent H. So this the resistive impedance of the transformer doesn't do phase shifting. Here we have 90 degrees the inductive X equivalent H phase shifting. And this is the voltage dropout, internal voltage dropout of the transformer, and you have you have well, you don't know how much is this. You need to know this value, but it's not important. Okay, now this is the voltage regulation. So if you bring 2200 volts in real life, so we said that this was a constant here. Now, why did we say that? Because we want to see what will be the real value of no load if we want to bring a 0.6 power factor lagging on the load. We need to know what will be the no load voltage. So if I, as a designer, know that the average area of your, I don't know, neighborhood uses 0.6 power factor lagging, you as an, or in average you calculated it, you want to make a new transformer, and then you will make a transformer which, when you bring 2200 volts on the high side, on the no load will be 230,694 on the secondary. And when you know that the 0.6 power factor lagging is on the secondary, then it will decrease from 230,694 to 220, because all your motors, fans, everything you have in your household, if you are in Europe, works on 220 volts, for example. And yeah, this was for the power factor lagging, and you will do for the power factor leading, and I will leave you to do that. What do you have to do for this IH, or when you had cosine minus 53,13, now you just use plus sign 53,13 degrees, and you just you don't get minus J 2,727, you have plus. Now this is for B. You have a plus. The equivalent impedance stays the same of the internal transformer. This now is not 2306,94. Now this is for B, when you have power factor leading, so more capacitive power, you get 2137,9, and the phase angle here is 2.48 degrees. So this is for leading. Now the voltage regulation is now 2137,9 minus 2200 divided by 2200, and then you get minus 2,82%. Now what this means is, if you want to have when you have a load, if you want to have if you have a power factor leading, now you have to bring you have to have a no load voltage of 213,79, not 2000, because this is the referred value. So this means if you bring on a power factor leading of 0,6, then this here will rise from 213,79 to 220 volts on the output for a power factor leading. And now let's the phasor diagram for power factor leading. Now this was for lagging, and now we have a leading power. Now here we have the I'm gonna write it down a little bit here. So here we have a low terminal referred on the primary side, 2200 volts. Now you have power factor leading, so the current is here, something like this, and the phase, the angle here to here is plus 53,13 degrees. So plus, not minus. And the voltage now is shifted for not 0,9, but from here to here the angle is 2.48 degrees, and the value is a little bit smaller now, 2137.9 volts. So this here, its magnitude is much higher. Now you have a resistive load, a reactive, and the equivalent impedance. I hope you're so minus 2,82 degrees. That means you have power factor leading, and then the voltage will rise on the output if you connect. If you have 213,79 volts on the output, the no load, so you didn't connect any load. Then if you connect the 0,6 power factor loading on the secondary side, 230,79 will rise to 220, and there will be phase shifting for 2.48 degrees. Okay, I hope you understand now voltage regulation, and engineers always see what is the phase shifting. They have the diagram if they work in an electrical distribution company, and they also regulate all of this stuff. Now the best thing is to have a power factor of 1, but that's not usually the case, so some precautions are then taken. Thank you for watching, and see you in my next video. Bye.